Okay, so welcome to the University of Adelaide's Electrical and Electronic Engineering 1A Practical Impact tutorial for Module 3. Today we just want to have a quick discussion about RC time constants. Throughout the class you so far would have come across a switching circuit. Looks a little like this. Midway through the pack we pose you a question, why do we talk about this time constant 37%? Why is it useful? Well, to understand why, we have to go back to some pretty basic principles. What we want to go back is to start with is the discharge equation for a capacitor. Why? Because the maths is a little bit easier for this one. The current through a capacitor is given by the capacitance multiplied by dVc by dt, so that's the voltage across the capacitor differentiated with respect to time, which is also equal to the negative of the voltage across that capacitor divided by the resistance in series with it. Some of you might recognise this as a first order differential equation. Here I have written it in isolation. As such, it'll have the solution, this solution, an exponential decay curve solution form, which is voltage across the capacitor is equal to the initial voltage, in this instance it's Vs, supply voltage, assuming it's fully charged, times by the exponential of minus t by RC. If you have any problems getting from here to here, you'll need to go off and consult the mathematics department, possibly the Maths Learning Centre, because that mathematics falls outside the scope of this course. So, now that we recognise this as an exponential decay curve, looks like this blue one that I just sketched up on the graph over here, well, let's ask ourselves the question, well, where have we seen this before? Some of you might want to think back to Year 12 physics and possibly chemistry. We need to look at half-life decay and nuclear decay. You remember from there that this voltage curve, as an exponential curve, will never get to zero. So for us as engineers to say, when will this voltage across this capacitor get to zero? We can't answer that question. It's impossible. That said though, we still want to be able to describe like a period upon that voltage curve, a period of time along that voltage curve. So when will it get to a certain voltage? That is starts to be a useful question to ask, or a useful way to describe the behaviour of this circuit. So if we draw the analogy from physics, an equivalent would be half the original voltage. So substituting those values into our equation, we end up with Vc of t equals Vs, which is the initial voltage, divided by 2, equals Vs times by the exponential of minus t upon RC. Eliminating Vs's terms, we end up and taking the natural log of a half that's left over. We end up with log of a half equals minus t upon RC. If we're using our log rules, you end up with minus log of 2. Cancelling minuses both sides and dragging the natural log to the other side, we end up with t equals RC times by the natural log of 2. Now, for those of you not having a calculator in front of you, natural log of 2 is equal to 1.42. Easy enough, you might say. Beautiful. So I can now label this half point here as equal to RC times my natural log of 2. Great. Well, in my view, not so much. I've got better things to do in all honesty than remember what the natural log of 2 is. So instead, let's find an arbitrary value that makes the maths easy. So it's easy to remember. So let this arbitrary value be a. So we're looking, let's solve this equation now for Vc of t equals Vs upon a. So when does Vs come to a nice number? So Vs times by exponential of minus t upon RC. Well, we can crunch through the same algebra here and end up with this expression down here. And when this it comes out as being the answer of t equals RC times by the natural log of a. Now this I can set to 1 if, and hence t will equal RC, if and only if the natural log of a equals 1. That's the case when a equals e. E is 2.781828 for those of you playing at home without a calculator. And 1 divided by a is approximately 37%. So, hence the answer to the question. Along this decay curve, if we look at when this gets down to 37%, my answer down here is nice. Time is equal to RC, R times by C of the circuit. Much, much easier to remember. And that's how we look at describing those time constants in electrical engineering. Now, you can use the same mathematics to solve for the charging curve if you're that way inclined. It's the same process, but this is your starting equation here. VC of t equals Vs, all outside of 1 minus the exponential of minus t upon Rc. Sort of makes sense. You're asking yourself, well, when does this discharge curve that I'm making, if I subtract this off my initial value, when will it fully get to 0? It makes the maps across. All you do is you apply the same algebraic steps I've done through here to this equation, and that should pop an answer that you should find useful. I'm not going to do it though, because this video is already far too long. Have a good day.